Welcome to the boxing match of Cambridge Physics. In this explainer, we are giving you the ultimate exam strategy. Our motto today? Float like a concept, sting like evidence. Jab, cross, hook, those are your answer combinations to knock out the examiner's marking scheme. Look at the space shuttle launch on your screen. It's an incredible display of power and a classic past paper question across syllabus code 0625 and 9702. The question is, explain how a rocket accelerates in the vacuum of space, where there is literally nothing to push against. Let me introduce you to two typical students. First, we have Alex. Alex overloads his paper with raw physics facts, but offers absolutely zero analysis. He just writes, "Rockets have fire." Then we have Sam. Sam rushes through, completely missing the command word requirements, scribbling, "It goes fast because space has no air." If we look at their papers side by side, it is just a sea of red pen marks. Why? Because they don't understand the fundamental laws of motion, and more importantly, they don't know how to structure their answers for Cambridge.
So, welcome to this absolutely crucial session, the mechanics of reality, demystifying dynamics. I am so pumped to guide you through this strategy today. We are going to be exploring the literal mechanics of reality, turning those red crosses into green check marks. If you are sitting your Cambridge exams, whether that's syllabus 0652, 0654, 0972, or 5054, and you want a direct, structured understanding of the invisible forces that dictate how our physical universe operates, you are in exactly the right place. We are going to build your physics success blueprint right here, right now.
Okay, let's dive into our roadmap for today's session. Consider this your cheat sheet for dynamics. We'll start in the ideal world to lay down Newton's foundational rules and decode what examiners actually want when they ask about them. Then, we'll clear up a massive everyday misconception in mass versus weight, a trap that catches out thousands of students every year. After that, we're running an interactive workshop on what happens when things get complicated in the messy reality of friction and drag. Finally, we'll lock in your top grades by looking at the universe's strict ledger system in cosmic accounting, focusing on momentum and collisions.
Section 1. The Ideal World and Newton's Rules of Motion. This is where we lay the foundation for your exam combinations. Let's get ready to rumble.
To really grasp how things move and how to score full marks on dynamics history questions, we have to look at the progression of ideas. For almost 2,000 years, Aristotle had everyone convinced that resting was an object's only natural state. He thought you always needed a force to keep something moving. But Galileo came along and hit that theory with a massive hook, suggesting that moving at a constant speed is just as natural as sitting still, as long as there is zero friction. Enter Isaac Newton. He took Galileo's brilliant insights and completely revolutionized physics. Understanding this shift is vital because exam questions often test your ability to contrast these models, specifically testing assessment objectives related to the evolution of scientific knowledge.
So, Newton distilled this into 3 elegant laws, and here is how you need to frame them for the examiners. First, inertia. Every object continues in its state of rest or with uniform velocity unless acted on by a resultant force. Second, if you do apply a resultant force, it causes acceleration. And third, whenever one object exerts a force on another, the second object exerts an equal and opposite force on the first. Now let's break down the command words. If the paper says state Newton's first law, you just give the definition. But if it says explain how Newton's third law applies to a collision, that is where students like Sam lose marks. You cannot just rush it, you need to analyze the specific scenario.
This brings us to the bedrock equation. Force equals mass times acceleration. F equals ma. 1 Newton of force gives a 1 kilogram mass and acceleration of exactly 1 meter per second squared. Now, how do top students write about this? They use the Peel framework. Point, evidence, explanation, link. Your point is the law. Your evidence is the formula, F equals ma. Your explanation is showing how the specific mass limits the acceleration. And your link ties it back to the question. This Peel framework is your jab, cross, hook. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Which brings us right back to our cold open question and our struggling students, Alex and Sam. Why does the space rocket move in a vacuum? Let's rewrite their answers live using the Peel framework. Point, the rocket moves due to Newton's third law of motion. Evidence and explanation, the rocket expels exhaust gases backwards, exerting a massive downward force on them. Because every action has an equal and opposite reaction, the gases exert a forward force of the exact same magnitude on the rocket. Link, Therefore, the rocket doesn't need air to push against, it is actively pushing against its own expelled mass, causing it to accelerate upwards. Boom! That is a full mark answer. Red pen marks just transformed into green check marks.
Moving on to Section 2, Mass versus Weight, clearing the confusion. This is where we implement the next step of our physics success blueprint.
Let's tackle a trap that examiners set in almost every single Paper 1 multiple choice section. Look at the split screen here. We have a top hand balance and a lever balance. Alex would look at these and say, they both weigh stuff. Wrong, 0 marks for Alex. A top hand balance actually measures the gravitational force pulling an object down against a spring. That is weight. A lever balance, on the other hand, pivots to compare an unknown mass against calibrated masses. It relies entirely on equilibrium and operates independently of the local gravitational field strength. If you took both of these to the moon, the top hand balance would give a different reading, but the lever balance would stay exactly the same.
The terminology trips people up constantly. You must clearly distinguish these in your definitions. Mass is a measure of an object's inertia, its resistance to acceleration, measured strictly in kilograms. Weight is the actual gravitational force acting on that mass, calculated as W equals mg, measured in newtons. When you buy 5 kilograms of mangoes, the commercial scale says 5 kilograms, but it's measuring weight. In exam terms, that 5-kilogram mass actually has a weight of roughly 49 newtons on Earth. If you mix up kilograms and newtons, the examiner will penalize you instantly. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3, the messy reality of friction and drag. It is time for our interactive workshop, so get your pens ready.
Welcome to Challenge 1, the data scan. I am putting a complex physics timeline on your screen right now, and I'm starting a 60-second visual countdown timer. Your job is to extract the core trend here about an object falling through a viscous fluid like air. Go. Look at Step 1, release. The only force is gravity, so it accelerates at g. Now scan Step 2, falling. As velocity increases, what happens? The viscous drag force pushing back against it builds up. The net force decreases, so acceleration drops. Finally, Step 3, equilibrium. The upward drag perfectly matches the downward weight. Acceleration is exactly 0. Time's up. If you extracted that velocity increases while acceleration decreases until it hits 0, you just secured 3 marks.
Now for Challenge 2, find the flaw. Look at this parachutist. I'm going to read a flawed sample paragraph, and I want you to shout out the sentence that loses the mark. The parachutist jumps and gravity pulls him down. As he speeds up, air resistance increases. When air resistance equals his weight, he stops moving. Did you catch it? Yes, he stops moving is the flaw. Sam wrote that, and Sam lost the mark. Here is the examiner commentary. When upward drag equals downward weight, the resultant force is 0. According to Newton's first law, an object with 0 resultant force continues at a uniform velocity. They don't stop falling, they just stop accelerating. This constant speed is terminal velocity. Always use the term constant velocity, never stops moving. Section 4, Cosmic Accounting. We are diving into momentum and collisions. This is usually the highest weighted section in your Paper 2 structured questions. Let's talk about the strictest bookkeeping system in the universe. The currency here is linear momentum. It is a vector quantity, defined simply as the product of an object's mass and its velocity. The formula is P equals mv. The golden rule you need to memorize word for word is the principle of conservation of momentum. For a closed system, in any direction, the total momentum before an interaction is exactly equal to the total momentum after the interaction. If no external forces act on an isolated system, the total momentum remains perfectly constant. You can trade it between objects, but you absolutely cannot destroy it. This is your anchor point for any collision question. So what happens during collisions? Cambridge expects you to distinctly compare 2 types. In perfectly elastic collisions, both momentum and total kinetic energy are totally conserved. But in our macroscopic world, we mostly deal with inelastic collisions. Think of a squelching lump of clay dropping onto the floor. It hits and sticks. Momentum is conserved if you include the Earth in your system, but massive amounts of kinetic energy are completely lost. Where does it go? The examiner wants you to explicitly state that it is transformed into thermal energy or heat and sound. If you just write energy is lost, you get 0 marks. You must say kinetic energy is transformed into other forms. Now, Get ready for Challenge 3, Speed Writing. We're going to look at how to change momentum using the concept of impulse, which is force multiplied by time. Look at this tennis serve. The ball is in contact with the racket strings for only 25 milliseconds. To radically change the momentum of that 60-gram ball and fire it off at 55 meters per second, the racket exerts an average force of 130 newtons in that tiny fraction of a second. The relationship here is that force equals the rate of change of momentum. Keep that in your head, because I'm about to test you on a much more extreme scenario. Here is the speed writing prompt. A golf club impacts a ball for only 3.0 milliseconds. That is radically less time than the tennis racket. The club needs to accelerate a 45-gram golf ball from rest to a velocity of 40 meters per second. Look at the on-screen timer. I am giving you exactly 30 seconds to write one perfect PL paragraph calculating the force and explaining the relationship between contact time and force. Go! Remember your command words. Show you're working. Convert your mass to kilograms. Convert your milliseconds to seconds. The clock is ticking down. 3, 2, 1. Pens down.
Let's look at the answer. The crucial number you should have calculated is exactly 600 newtons. Here is the feedback. Your point, impulse, equals change in momentum. Your evidence, force, equals the change in momentum divided by time. So, 0.045 kilograms times 40 meters per second divided by 0.003 seconds. Your explanation. Because the time frame of the impact is so incredibly short, the average force exerted by the golf club must be massive. Your link. This proves that for a given change in momentum, the shorter the time interval, the massively greater the force applied. If you got 600 newtons and explained the inverse relationship, you just secured an A-star grade on that question. Bringing this explainer full circle, look at this progress bar on screen reaching 100%. You now have the complete physics answering system. 3 rules guarantee top marks. Number 1, command word decoding. Number 2, strict PL framework application. And number 3, the time management matrix. Remember Newton's first law. Every object continues in its state of rest or with uniform velocity unless acted on by a resultant force. All motion is a constant negotiation of forces, and dominating your exam is a constant negotiation of strategy. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
Before we completely wrap up, I want to leave you with one final, provocative thought experiment to test your cosmic accounting skills. Picture 2 ice skaters standing facing each other on completely frictionless ice. One has a mass of 80 kilograms, the other is 65 kilograms. If the heavier skater pushes the lighter partner away, who actually moves away faster, and why? Apply Newton's third law, apply the conservation of momentum, and try writing out your answer using the PEL framework we learned today. Put your answers down in the comments, and I will personally review them. Thank you so much for joining me in the ring today to demystify dynamics. Keep jabbing at those past papers, keep asking questions, and as always, keep learning. See you in the next one.